Hi everyone. Today let's continue our class. So today we're going to cover the electric potential. But first, before we start the electric potential, let's first look into the curve of electric field. So now let's calculate the curve of E. So let's start the divergence in the previous equation by first considering the simplest case, which is a point charge at the origin. So in this case, the electric field could be calculated using this equation. So we have derived this equation in previous lectures. So that's very simple equation, and it's Coulombic equation. So if you take a look at the potential, which is shown here in figure A and B, you will see intuitively you can see there's no curve, no curl. So the curl should be 0, but let's prove it quantitatively. So now let's do an integral from A to B to calculate the line integral of E. So let's look at the figure on the right. If you have a figure like that, so this is the x, y, z coordinates. You have E, which is a vector electric field in the space, and you want to do a let's say line integral from one point to another point, which is from A to B. Then what we can do is let's use E from this equation, and then dl equals to this expression. So this equation has been derived in previous lectures in the spherical coordinates. If you forget it, you can go back to the chapter 1 to see how did we derive the dl equal to such a equation in spherical coordinates. So in this case, E dot dl becomes this equation. And therefore, okay, let me use the pencil. Therefore, if you do the integral from A to B, 4 pi epsilon 0, 1 over 4 pi epsilon 0, of course, it's a constant. You can take it out from the integral, and you can just do the integral of this part. And then finally, you can get the integral to be this form. That's not a very difficult integral. It's just a normal integral. So let's look at this equation. What did you find? You will see actually the line integral, even it depends on path. For example, in this figure, you choose a path from A to B in this way. But however, once you calculate the integral, you will find at the end, it's independent from the path. You just get the equation of 1 over 4 pi epsilon and then Q over RA subtracted by Q over RB. There's no information about the path. It only depends on your RA and RB. So it only depends on your starting point and the ending points. So in this case, let's say this is from A to B. If you do the same thing from B to A, then you get a negative or negative value of this equation. Let's say if you do B, do the integral from B to A, E dot dl, all of them are vectors. you will get something negative to what you get here. And then if you do integral of a to b plus b to a, it should be 0. So this is integral of a to b. This is integral of b to a. It should be 0. So an integral from a to b, then b to a means you have done a circular integral. Because you can imagine, let's going back to this line integral. You first do an integral from a to b, and then you do a integral from b to a, then that's a whole circle. Then that means a closed path is 0. And then applying Stokes' theorem, you will get the curl of E equals to 0. Okay, so by now we have proved that the curl of electric field is 0 when this electric field is generated by a point charge, because remember we start from this equation. This is generated from a point charge. And if there are more than one charge, we know the electric field could be calculated by the sum of the electric fields generated by each of the charges, which is E equals to E1 plus E2 plus E3. So E1, E2 means the electric field generated by Q1, Q2. So in this case, we can demonstrate the curl of the total E, which is generated by multiple charges, is also 0, because the curl of each electric field generated by each charge is 0. Then even you do a sum, vector sum, and get the total electric field E, and then if you do the curl of this E, you will get still 0 plus 0 plus 0, you will get finally 0. So any static charge distribution follows this rule. The curl of the electric field is 0. Okay, so this is the curl of electric field. Now let's start to introduce another concept, which is potential. The electric field E is not just any old vector function. It's a very special kind of vector function because the curl of E is 0. So we're going to exploit this special property of electric field to reduce a vector problem to a much simpler scalar problem. The first theorem in previous section 1.6.2 tells us that any vector whose curl is 0 is equal to the gradient of some scalar or scalar function. Then what we're going to do is trying to find out this scalar or scalar function for the electric field E. And we will demonstrate that this scalar is the potential or electric potential. Okay, so because the curl of E is 0, the line integral of E around any closed loop or circle is 0. And it can be written in this equation. So a closed path, integral of e should be 0. And the line integral of e from a point A to B is the same for all paths. Let's say if you have a point A here and a point B here, you have infinity numbers of paths connecting A and B or going from A to B. Then in this case, if you do a line integral of E, then we have demonstrated it's independent from paths. No matter which path you choose, the value of the integral is always the same. Okay. So the line integral of E from point A to B is the same for all paths. Because the line integral is independent of paths, we can define a function. Let's define a function which is VR to be the negative integral, the negative line integral of E, which is from phi to R, or from a reference point to the position R. Here, the reference point is some standard reference point on which we have agreed beforehand. V then depends only on the point R. It's called the electric potential. Let's say here is A, here is B. We can define a reference point phi here. Then you can do an integral from, let's say, phi to A. Then that's the potential. That's the electric potential of A. And then you can do the same thing from this reference point to B. You can do an integral from this point to B, and then you get electric potential of B. And then we'll demonstrate if you use electric potential of B subtracted by electric potential of A, you will get the electric potential between A and B, no matter which reference point you choose. You could choose the reference point to be here, or you can choose the reference point to be here. It doesn't matter because the difference between A and B should always be the same. Difference of the electric potential between A and B should be the same, no matter which reference point you choose. But for convenience, usually we choose infinite far away as our reference point. Now let's see. Here the reference point is some standard reference point on which we have agreed beforehand. Then the potential difference between 2 points A and B could be calculated in this way. So since we have defined the electric potential to be negative integral from reference to R, then let's use the definition of VB and VA. So this is VB subtracted by negative VA, which means plus this term. And then, so this is from reference to B. This is from reference to A. If you change the sign, make it negative, it could be, it should be from A to reference. And then it becomes line integral. Let's say if this is A, this is B, this is your reference point. So first, you do a reference, you do a line integral from reference point to B, which is from here to here, and then from A to reference point, which is from here to there. If you sum them up, it becomes from A to B, because we know it's path independent. So if you do an integral from A to phi and then phi to B, it equals to an integral from A to B. So you get this integral from A to B. And then now the fundamental theorem for gradient states that VB subtracted by VA equals to the integral from A to B of the line integral from A to B of the divergence of V, because we have defined the divergence of V should be negative E. So so the integral of divergence of V equals to the negative line integral of E. And finally, this is true for any points of A and B. The integrands must be equal. E equals to negative divergence of V. Okay, so this is the definition and some features of electric potential. Now let's see some comments on the electric potential. So first, as a name, so we name it as potential. It sometimes reminds you of, let's say, potential energy. But actually here, this potential doesn't mean energy. It's just the electric potential. It's independent definition from potential energy. Second, the advantage of potential formulation. Okay, so you can see easily, you can easily get E, just take the gradient from E equals to the negative gradient of V. So E is a vector, but V is scalar. So it seems like your gradient of scalar get a vector function. It seems like very impossible, but actually even E is a vector. It's not completely free vector because the vector of E has some restrictions. For example, the curl of E equals to 0. So it's not completely independent by, it's not completely free of vector. So E has some restrictions like the curl equals to 0. The curl equals to 0 means such conditions. So E is a very special kind of vector. So what potential formulation does is to exploit this feature to maximum advantage, reducing the vector problem to a scalar one in which there's no need to fuss with components. Okay, next, the reference point. So when you calculate the difference of the potential between 2 points, let's say A and B, it doesn't matter which reference point you choose. For example, you can choose the reference point to be some position, let's say phi. You can also choose it to be phi prime. Then your V, or the potential prime, should be the integral, negative integral from phi prime to R, or it could be from phi prime to phi and then phi to R, because remember that the line integral of E, it's path independent. So this equation is true. And you can say from phi prime to phi, the integral, you can define it to be K, which is constant. So if you choose, or if you change the reference from one point to another point, the electric potential actually is only changed by a constant K, and K equals to this integral. And the other part is VR, which is still the electric potential in the case of reference to be the original phi. So where k is just a constant, or the line integral from line integral of E from the old reference to the new reference. So V, let's say the V prime B subtracted by V prime A should be exactly the same as VB subtracted by VA, because the constant K and K will be canceled in the left hand. So if we define the potential difference from A to be delta V, then no matter you choose the reference of phi or a new reference phi prime, then the delta V doesn't change. So delta V prime equals delta V. So the reference is not so important when you calculate or when you consider only the potential difference for 2 points. But generally, when we choose the reference point, usually we set the reference point to be infinite. For example, if you have a charge here, which is positive Q, you want to calculate some potential A or some potential at point B. The reference point that you choose is usually here, infinity. So you define the potential at infinite location to be 0, and then you calculate the potential of A or B. But most of the case, you don't care too much about the potential of A or the potential of B. So in most cases, we care about the potential difference between A and B. Okay, potential obeys the superposition principle, because as we discussed before, if you have multiple charges, the net force could be calculated by the sum of forces generated by individual charges if you have multiple charges. So F equals to F1 plus F2 plus all forces. The same thing for electric field. Your net electric field equals to the sum of all the electric field by different charges. Integrating from common reference point to R, it follows a potential also satisfied principle. So the potential at any point also equals to the potential, the sum of the potentials which are generated by multiple charges. So V equals to V1 plus V2 plus all the V components. Okay, last, the unit of potential. In our unit, the force is measured in newtons and charge in coulomb. So the electric field are in newtons per coulomb. Accordingly, the potential is Newton meter per coulomb or joules per coulomb. A joules per coulomb is defined as a volt. This is also a very common unit that we're using in daily life. So note that the voltage of our, let's say, electric circuit is 110 volts. That's the same unit. Okay, now let's solve a problem together. Find the potential inside and outside the spherical shell of radius r that carries uniform surface charge. Okay, surface charge. Set reference point at infinity. So by default, we set the reference point at infinity. Means the potential at infinity is 0. Okay, so first, from Gauss law, the field outside is E equals to this equation. So we have solved this equation by using Gauss law in previous lecture. It's also Coulombic equation. But remember that this equation is true only when the field is outside. When it's inside, we cannot do this um, because if there's a point inside, that's a surface charge sphere. So if we draw a Gauss surface inside, you figure out there's no charge at all in the closed spherical surface, and the field should be zero inside the sphere. So Q is the total charge on the sphere, and the field inside is zero. The field inside is zero because you can still use the Gauss law. You draw a Gauss surface. There's no charge at all in this surface, so there won't be any electric field in or on this surface or on any other Gauss surface. Let's say if you draw another surface, there shouldn't be any electric field. So inside the entire sphere, there's no electric field, or the field is zero. Now, first, let's calculate the point outside the sphere. From outside the sphere, V equals to negative the line integral of E. And we set the reference to be infinity. So it's infinity to R. Infinity to R, and E times dl. E dot dl, we have calculated this equation many times, which has been shown in this slides here. So E dot dl equals to this equation, because dl is this equation. So dl has components in r direction, theta direction, phi direction, but it's a dot product. So theta direction and phi direction, they're zero when you do the dot product with E, because E is only in the r direction. So E dot dl, you have this equation. It's a scalar. So here you get the same thing. You can calculate this integral. You will have this equation, the difference of this equation of r prime from infinite to r. When it's infinity, so this equation becomes zero. When it's r, this equation becomes this. So the potential equals to this equation. And then now let's find the potential inside. When it's inside, we must break the integral into two pieces. One is from infinity to the surface, and then from the surface to the inside point. Okay, now let's break it into two parts. First, from infinity to r, or to the surface. Second, from the surface to r, which is inside the sphere. So here, the first term we have calculated. It's shown here. The only difference is now this r becomes the capital R, which means the radius of the sphere. For the second term, we have talked about it. The E inside the sphere is zero, so this term is zero. So finally, you will get the potential inside the sphere becomes 1 over 4 pi epsilon 0 Q over capital R. So notice that even the potential is zero in the shell or in the sphere. Even the field is zero in the shell. The potential is non-zero. The potential is the same as the potential on the surface of the sphere. Okay, now Poisson equation and Laplace's equation. Okay, we found in section 2.3.1 that the electric field can be written as a gradient of a scalar potential. This is E equals to negative the divergence of V. So the equation arises, what do the divergence and the curl of E? So we have demonstrated before the divergence of E equals to rho over epsilon 0. Rho is the charge density, and the curl of E is 0. And if we don't use E, instead, if we write the equation by using V, because V and E, they have this relationship, then what we can do is first divergence of E equals divergence of negative divergence of V, which is negative divergence squared V, or the divergence of E is a Laplacian of V. So the Gauss law becomes the del squared V equals negative rho over epsilon 0. So it's derived from these two equations. This equation is known as Poisson's equation. So Poisson's equation tells us the relationship between a V, or the potential, and a rho, the charge. In regions where there's no charge, rho equals to 0. Then this equation becomes Laplacian's equation, which is del squared V equals to 0 if rho is 0, or if there's no charge. Then Poisson's equation reduces to Laplace's equation. So that's for Gauss law. Now let's look at the curl law. The curl of E is 0, means the curl of negative del V is 0. So this is the curl law when we describe the curl of negative del V. So if you know the potential V, and then you know the curl of negative of divergence of E should be 0. Okay, the potential of localized charge distribution. So we defined V in terms of E. So we know the relationship between V and E. Ordinarily, it's E that we're looking for usually, but sometimes it's easier to first calculating V and then derive E. So the idea is that it might be easier to get V first and then calculate E by just taking the gradient. Then the Poisson's equation relates V and rho. Now let's see how to use Poisson's equation to describe relationship between V and rho to calculate V when you know rho, or calculate potential when you know the charge distribution. Because if you know the charge distribution, and you can calculate the potential, and then you can easily calculate E. E is just the gradient of the potential. Okay, now let's see. The electric field is E equals to this equation. We have derived it before. And dl is this equation. Again, this is the dl expression in the spherical coordinates. So E times dl equals to this equation. Setting the reference point at infinity, the potential of a point charge Q at the origin is V equals to the line integral from reference point to R, and equals to this equation. So this equation has been, we have discussed this entire calculation in this example. So here we don't want to describe it again. So the result of VR should be shown here in this equation. So this is the potential at position R when you have one charge Q. Let's say if you have one charge Q and you want to calculate the position P, and the vector between Q and P is R, then you get this equation, or shown here, 2.26. So where R is the distance from Q to R, then the potential of collection, okay, so this is just for single charge. If you have multiple charges, Q1, Q2, until Qi, you want to calculate P, what you can do is you can do a sum of the potentials generated by each charge, which could be described in this equation. This is the sum of potentials generated by Q1, Q2 until Qn. And for a continuous distribution, let's say here it's continuous charge distribution, instead of doing the sum of multiple charges, here you need to do a volume integral. Let's say V equals to an integral of the charges instead of a sum of charges. If it's a volume integral, of course, it should be volume density times d volume. If it's line charge, it becomes a line density, the line density of the charge times dl. If it's a surface charge, then it's a surface charge density sigma times dA, which is a small piece of the surface. So that's the electric potential calculation for continuous charges, no matter it's a volume charge or line charge or surface charge. You can look at the equation of 2.29 and 2.30. Okay, now if we do a comparison between, let's say, 229 and the equation of electric field, you will see for electric field, we have calculated before, it's 1/4 pi epsilon 0 rho over r squared and times the direction of r d tau. If you compare these two equations, the electric field and electric potential equations, they are very similar. So the constants are the same. The only difference is here in electric field, you get 1/r squared, but in potential, you get 1/r. And then electric field is a vector. The direction is the uniform vector of r, but for the potential, it's a scalar. It doesn't have any direction. So that's the difference between potential and electric field. Okay, so that's all for today. So we have introduced the electric potential and also introduced a little bit about the curl of electric field at the beginning of the class. So please read the textbook by yourself and solve the problem of example 2.8. That's not difficult problem. Please just look into this problem. We don't introduce the derive of the equations on class, because in the textbook, it gives you very detailed the steps of how to derive and how to solve the problem. It's in very detailed descriptions. So please read it. And then that's all for today's class. Thank you.